In this video, we are given an orthonormal basis for Rn. And then we're going to let set S be the span of the first k vectors in U. And we're going to let T be the span of the remaining vectors in U. And then if we take any vector in S and any vector x in S and any vector y in T, is going to be true that x dot y is going to be 0. So I think it's best to figure out what we're going to call x and what we're going to call y, and then compute the dot product, or at least talk about the dot product. Okay, so if x is in the span of S, then for some scalars C1, C2, up to CK, x is equal to C1U1 plus C2U2 all the way down to C sub k U sub k, and for some scalars C sub k plus 1, C sub k plus 2, all the way down to C sub n, y is ck plus 1, U sub k plus 1, plus C sub k plus 2, U sub k plus 2, all the way until C n U n. So now x dotted with y, well, it's x, which is this, dotted with y. Well, let's write that down. It's C1U1 plus C2U sub 2 all the way down to CK U sub k, dotted with C sub k plus 1, U sub k plus 1, plus CK plus 2, UK plus 2, all the way down to C sub n, U sub n. Now notice, the subscripts of the U in the x vector only go from 1 to k. In the y vector, oops, I meant here, in the y vector, they're all bigger than k. They go from k plus 1 up to n. So now, what will an arbitrary vector, what will an arbitrary entry in the dot product be? Now remember, we're going to dot this with this whole thing. We're going to dot this whole thing with that. We're going to dot it with all the ones up to here and the ones in between. We're also going to now dot this with the first and the second all the way up to the last, and then ultimately we'll dot the last with the first, the last with the second, and the last with the last. Okay, so let's look at any arbitrary one. Take any arbitrary term in this dot product. Such as C sub I, did I come up anywhere? No. C sub I, U sub I, dotted with C sub j, U sub j, where I is contained in 1 through n, and j, 1 through k, that's the key part, and j is in uk+1 through n. Note, I intersect j is the empty set. Well, actually, I was not that set. I was in that set. Notice that the two sets that the i's and k's, i's and j's are coming from, they are disjoint. They have no elements, they have no elements in common. They equal the empty set. I mean, after all, this is 1 through 50, the integers, and this is from 51 to 100. They have nothing in common. Okay. Now, CI/UI dotted with CJ/U sub j. This is equal to CI/CJ times UI dot UJ. We proved that in their video on properties of dot products. And what we get here is C sub I, C sub j times the 0 vector, because U, where these vectors came from, these vectors came from, did I name that set U? Yeah. The vectors from this set is from an orthogonal set. Fine, orthogonal basis, but the vectors in there are orthogonal. So the sorry, I take that back. Orthonormal. They're orthonormal. That means that any two dot products of different vectors in U give you 0. Okay, so what we have is an arbitrary term in this dot product. An arbitrary term in this dot product. For example, C2U2 dotted with CK+1 UK+1 is 0. I actually didn't finish and say 0. So each term in x dot y is equal to 0. That implies that x dot y itself is 0. Because if you add up zeros, you get 0. X dot y is our sum. This plus this plus this plus this plus this, eventually to plus that. And these are the terms. The terms are what you are adding. And if each term is 0, if each and every term is 0, well, when you add them up, you're going to get 0. And basically, that completes the proof. Because I concluded that x dot y is equal to 0. If you like videos like this, please subscribe to my channel, like this video, and most of all, ask your friends and family to subscribe. See you guys in the next video. Watch and learn.